A register-to-register transfer is like handing a ball from one child's hand to another without touching the floor. In a CPU, registers are tiny, super-fast storage slots like a child's pocket. The instruction MOV R1, R2 tells the processor to copy the value that is currently in register R2 into register R1. No memory is involved, so the move happens in a single clock cycle. Think of it as swapping stickers. You look at the sticker in pocket 2 and simply place a copy into pocket 1. Because the hardware knows exactly where both pockets are, the move costs almost no time and no extra effort. Mathematically, if R2 equals V, after MOV R1, R2 we have R1 equals V. No change to R2 occurs. This is the most basic data movement operation and forms the building block for more complex code. Immediate operand loading is like giving a child a brand new toy straight out of a gift box, instead of taking it from another child's hand. The instruction MOV R3, #0x3f says put the constant value 0x3f, 63 decimal, directly into register R3. The hash symbol marks the number as an immediate value, meaning it is encoded inside the instruction itself. The CPU does not need to fetch the number from memory. The value travels together with the opcode like a sealed envelope that already contains the toy. This makes the operation fast, usually one clock cycle. In math terms, if the immediate constant is C, after execution R3 equals C. For example, MOV R0, #10 makes R0 hold the number 10, ready for later use. This technique is especially handy when initializing counters, setting flags, or loading small constants. Memory addressing modes decide how the CPU finds a specific piece of data in its huge toy chest memory. Direct addressing, the instruction contains the exact locker number where the toy is stored. Example, move R4, open bracket 0x200 close bracket tells the CPU to go straight to address 0x200 and copy that value into R4. It is like a map that points directly to a shelf. In direct addressing, the instruction points to a locker that holds another locker number. Example, move R5, open bracket R6 close bracket means look at the value inside register R6, treat that value as a memory address and fetch the data from there. This is like a note that says the toy is in the locker whose number is written on the paper you are holding. Indexed addressing, a base address is combined with an offset index. Example, move R7, open bracket base plus x close bracket. If base equals 0x3000 and x equals 4, the CPU accesses 0x3004. Think of a row of cubby holes where you start at a known start point base and then walk a few steps index to the exact spot. Mathematically, the effective address EA is computed as direct EA equals constant address. Indirect EA equals contents of register, EA equals RN. Indexed EA equals base plus index. These modes give programs flexibility in handling arrays, tables, and pointers. Parallel I/O port access is like having a set of doors that can be opened or closed all at once with a single push of a button. In microcontrollers, an I/O port is a group of 8 or more pins that can be read from or written to together. The instruction out port R0 copies the whole 8-bit value in R0 to the physical pins of port A in one step. Every pin changes at the same moment, just like pulling a lever that flips many switches simultaneously. Similarly, in R1, port B reads the current state of all pins on port B into register R1. This is useful when you want to light up a whole LED matrix or read a set of buttons at once. The operation is performed in a single bus cycle, so there is no need to move each pin individually. Think of sending a whole word of a sentence to a friend in one envelope rather than mailing each letter separately. Because the hardware moves the whole byte in parallel, the timing is predictable. One write or read typically costs one clock cycle plus any required setup time. A stack is like a pile of trays in a cafeteria. You add new trays on top and take the top tray when you need it. The CPU uses a special region of memory called the stack for temporary storage, function calls, and return addresses. Push R2 puts the current value of R2 on top of the stack, moving the stack pointer down or up depending on the architecture. It is like placing a tray with a dish onto the pile. Pop R3 removes the top tray and gives its dish to R3, simultaneously moving the stack pointer back. This restores a previously saved value. Call subroutine does two things. It pushes the address of the next instruction, the return address, onto the stack, then jumps to the label subroutine. It is like writing down where you left the cafeteria, placing that note on the stack, and walking to a new kitchen station. Ret pops the return address from the stack and jumps back to it, resuming where you left off. Mathematically, if SB points to the top of the stack after push X, MEM of SB-1 equals X SB equals SB-1. After pop Y equals MEM of SB, SB equals SB plus 1. The stack guarantees that data is retrieved in the exact reverse order it was saved, last in first out, which is essential for nested function calls. Using the stack keeps registers free for calculations and ensures that each function gets its own safe place to store temporary values. Explanation: multi-byte transfer deals with moving more than one byte at a time, like carrying a whole stack of books instead of one page. In 16-bit CPUs, a word is 2 bytes 16 bits, and in 32-bit CPUs, a double word is 4 bytes 32 bits. When you execute move AX from address 0x1000, word move, the processor reads two consecutive bytes from memory addresses 0x1000 and 0x1001 and places them into the 16-bit register AX. The order of those bytes matters. This is called endianness. Little endian used by Intel. The least significant byte, LSB, is stored at the lower address. So if AX equals 0x1234, memory contains 0x34 at 0x1000 and 0x12 at 0x1001. Big endian used by some network protocols. The most significant byte, MSB, is at the lower address. The same value would store 0x12 at 0x1000 and 0x34 at 0x1001. For a double word move like move EDX from address 0x2000, 4 bytes are transferred respecting the same ordering rule. If you need to swap endianness, you can use byte swap instructions, bswap, or manually shift and mask. Convert little endian to big endian in E, a X move EBX from E, a X shift right EBX by 24 bits to bring byte 3 to low position. Shift left EAX by 24 bits to move byte 0 to high position, and similarly handle the middle bytes. Understanding endianness is crucial when communicating with other devices, for example sending data over a network, because both sides must agree on the byte order. The advantage of word or double word moves is speed. Moving 2 or 4 bytes at once reduces the number of bus cycles compared to moving each byte individually. Direct memory access, abbreviated DMA, is like hiring a moving crew to carry boxes directly from one room to another while you stay on the couch doing other work. Instead of the CPU reading a byte from memory and then writing it to a peripheral, which ties up the CPU each time, the DMA controller autonomously moves a block of data. Program the source address, write the start address of the data to a DMA source register. For example, move DMA SRC, #0x4000. Program the destination address, write where the data should go. For example, move DMA DSD, #0x8000. Set the transfer count, number of bytes. For example, move DMA count, #256. Configure mode, direction memory to peripheral or peripheral to memory, burst size, etc. Enable DMA, set DMA control, enable. Once enabled, the DMA hardware reads the source bytes and writes them to the destination without CPU intervention, often completing the whole block in fewer clock cycles than a CPU-controlled loop. Mathematically, if n is the number of bytes, CPU-controlled copy costs roughly n multiplied by the sum of read cycles, write cycles, and overhead. DMA costs setup cycles plus n multiplied by transfer cycles, where transfer cycles can be as low as 1 per byte, and the CPU is free to perform other tasks during the transfer. After the transfer, the DMA controller may raise an interrupt to tell the CPU that the job is done, similar to the moving crew ringing a doorbell when they finish. Using DMA is essential for high-speed peripherals like audio, video, or networking, where large data streams must be moved efficiently. Cycle-accurate timing means knowing exactly how many clock ticks each instruction consumes, just like counting each step while walking to a destination. Optimizing data transfer instructions therefore involves choosing the fastest path and arranging code so that the CPU never has to wait. Prefer register-to-register moves, they usually take one cycle. Avoid memory accesses when possible. Use burst or block transfers. Instructions like rep movs on x86 move many bytes with a single loop overhead, reducing per byte cost. Align data, placing frequently accessed variables on address boundaries that match the bus width. For example, 4-byte alignment for 32-bit accesses eliminates extra cycles caused by misaligned accesses. Pipeline awareness, modern CPUs fetch the next instruction while the current one executes. A sequence like mov R1, open bracket R2 close bracket followed by add R1, #1 can cause a data hazard. Inserting a NOP or ray ordering can keep the pipeline full. Utilize prefetch. Instructions like prefetch hint the CPU to load data into cache early, turning a future memory wait into a cache hit. Minimize branch penalties. Conditional moves, for example CMOV or branch free tricks, avoid costly pipeline flushes. Mathematical example. Suppose moving 256 bytes with a simple loop. For I equals 0 to 255, move AL, open bracket SRC plus I close bracket, move open bracket DST plus I close bracket AL. If each MOV costs 2 cycles, total cycles equals 256 times 2 times 2, which is 1024 cycles. Using rep movs, which copies a byte each iteration but with loop overhead reduced, might take about 1.5 cycles per byte. Total approximately 384 cycles, a 3-fold speedup. By counting cycles, aligning addresses, and selecting the right instruction forms, you can craft data transfer code that runs as fast as the hardware allows, which is crucial for real-time systems like motor control or audio processing.